Last time we saw that we could use critical numbers and endpoints to find absolute maxes and mins of functions. Today we are going to look at two different ideas related to what the first derivative tells us about functions. We'll look at where the function's increasing and decreasing, and this will be related to where we have local maxes and mins, not absolute ones. So the first question is, what does it mean for a function to be increasing, and what does it mean for a function to be decreasing? So let's just draw the function. And we can talk about increasing, decreasing. So maybe I have a function like this. So you might believe that this function is increasing here and here. So the way that I like to think about increasing is we always read from left to right, just like we would read English. So we read graphs in the same way. So if I start on the left-hand side of my graph, and if I was a little person walking along my graph, then the function will be increasing when I'm walking uphill and decreasing when I'm walking downhill. So in both of these blue regions, I'm walking uphill, and then in between over here, the function's decreasing, I'm going downhill. Okay. You could describe increasing as meaning that the y values get bigger as the x values get bigger. So that the f of x1 is greater than f of x2 if x1 is greater, is less than, sorry. No, I got my inequalities wrong here, sorry. So this should be that, there we go. So then we have x1, then x2, the y values get bigger as the x values get bigger. So the inequalities are the same here. This means this is when our function's increasing. So we see here, like this is my f of x1, this is my f of x2. And so as x got bigger, y also got bigger. The opposite is true for decreasing. Decreasing means that the y values get smaller as the x values get bigger. Okay, so if x2 is bigger than x1, then f of x2 should be smaller than f of x1. Okay, so this way of thinking about increasing, decreasing just kind of messes with my brain. Obviously, I get the inequalities backwards until I think about it hard enough. But we can use this to think about derivatives. So if I look at my graph here, in the blue regions, the slopes of the tangent lines are all positive. So notice if I looked at any tangent lines in this region here, draw my little tangent lines, these all have positive slopes. So it kind of appears as though the slopes of the tangent lines are going to be positive when my function's increasing. And then if I look at some of the places where it's decreasing, oh, these tangent lines all look to have negative slopes. So it might be the case that the slopes are negative when our function's decreasing. That indeed turns out to be the case. That's our increasing decreasing test. This is not a very fancy name. But this test says that if the derivative is positive, then my function is increasing. If my derivative is negative, then the function is decreasing. Okay, so this gives us a nice calculus way of determining where a function's increasing and where it's decreasing. So how are we going to use this? Well, we're going to figure out where the derivative is positive and where it's negative. In order to do that, we need to start out by finding where the derivative is zero. So we start out by, or does not exist. So we start out by finding the critical numbers. So that's the first thing that we're going to do. If I ask where a function's increasing and decreasing, find our critical numbers. So the derivative here, always start with the derivative if you don't know what to do. 6x squared minus 6x minus 12. I need to set this equal to 0. I can factor a 6 out of everything. And then I can factor this as x minus 2 times x plus 1. So my critical numbers are x is positive 2 and negative 1. Okay. Now, the way that I'm often going to deal with this is I need to figure out on what intervals my derivative is positive and where it's negative. So I like to do a sign chart for this. So I'm going to give a chart that gives me information about the first derivative. Make sure you label the sign chart. It both helps you remember that we're working with the first derivative here. It is also going to remind anybody looking at your paper that you know you're working with the first derivative. Okay, so I'm going to put my critical numbers on here, making sure I list them in numerical order, smallest number to the left, biggest number to the right. So I have my negative 1 and my 2. Now, what I'm going to do is I need to figure out for numbers less than -1, is the derivative positive or negative? Between -1 and 2, is the derivative positive or negative? And greater than 2, is the derivative positive or negative? We know that at -1 and 2, the derivative is 0, so the function's neither increasing nor decreasing at those critical numbers, and then we just have to figure out what's happening in between. So the way to do this is just pick a number on each of those three intervals that I've highlighted here and plug them into the derivative. So if I pick something bigger than 2, pick your favorite number bigger than 2, maybe like 3. If I plug 3 into my derivative, I want to know if I have something positive or negative. Using the factored form is usually a good idea. We notice that the 6 is always positive. 3 minus 2 will give me a positive. And then 3 plus 1 will also give me a positive. So I have three positive numbers multiplied together. I'm going to get a positive number here. Okay? So I'm going to put on the sign chart, I'm going to indicate a positive for that region. Okay? Now I need to pick a number between -1 and 2. 0 is a great choice. So I'm going to look at f prime of 0. When I plug 0 into that derivative, it's very easy to see that I get a negative number out. I don't care what the number is, I just care that it's negative. So I'm not even trying to figure out what the number is. So I get a negative on my sign chart there. And now I'm going to plug in a number less than -1, maybe -2. Okay, I'm going to again look at the factored form. 6 is always positive. -2 minus 2 is going to give me a negative. -2 plus 1 is also going to give me a negative. So I'm going to have a positive times a negative times a negative. That will give me a positive on my sign chart for the derivative there. Okay? So now I can read off of this sign chart what's happening. So my function f will be increasing where the derivative was positive. So the derivative was positive over here and over here, but not at -1 or at 2 because the derivative was 0 at those values. And the function will be neither increasing nor decreasing if the derivative is 0. Okay, so f will be increasing on the interval from -infinity to -1 and on the interval from 2 to infinity. Okay, notice I'm putting curly or not square brackets at -1 and 2 because we're not including -1 and 2. And this is, if I wanted to justify my answer, this is because f prime is positive. So the function is increasing when the derivative is positive. And then f will be decreasing everywhere else. Well, not everywhere else. In between here. I say not everywhere else because it's not going to be decreasing at those endpoints again. So it's decreasing from -1 to 2, not including -1 or 2. So decreasing on the interval from -1 to 2 because the derivative is less than 0 there. Okay? So this is what we're looking at to determine where our function's increasing and decreasing. Let's look at this graph and kind of see if there's anything more interesting that we can note. Okay, so I have the graph of our function f of x pulled up here. I had to zoom out a little bit, but we do notice that indeed this function is increasing up until it gets to -1, and then decreasing from -1 to 2, and then increasing for x greater than 2. So that's good. We also notice something interesting here that at -1, we have a local max. It's a local max because it's not the highest value. And then at -2 or at +2, we have a local min. It's kind of interesting to notice here that the function changes from increasing to decreasing at that local max and decreasing to increasing at the local min. That's not coincidental. So this is the next idea that we want to talk about, which also comes from looking at these sign charts, is that we're going to get local maxes and mins where the derivative changes signs. And if we think about that, if my function changes from increasing to decreasing, we're certainly going to have a local max. And if my function changes from decreasing to increasing, I'm definitely going to have a local min. And so the way that we can phrase that in terms of derivatives is if my derivative, and I'll write this down on the next slide in just a second, a little better. If my derivative goes from positive to negative, then we're going to have a local max. And that's because my function went from increasing to decreasing. And if my derivative goes from negative to positive, then my original function will have a local min because the original function went from decreasing to increasing. Okay. So if I look at this sign chart up here, I have a sign change at -1. The derivative, again, we're always reading from left to right. The derivative changes from positive to negative. So f will have a local max at x equals -1. And then the derivative goes from negative to positive at x equals 2. So my function goes from decreasing to increasing. So f will have a local min at x equals 2. Okay, so this sign chart for the first derivative tells us both where my function's increasing and decreasing and where my function has local maxes and mins. Okay, this idea of the local maxes and mins is called the first derivative test. So the first derivative test tells us if I look at a critical number of a continuous function, if the derivative changes from positive to negative at that point, so if my sign chart for f prime looks like this, then we have a local max. If my sign chart goes from negative to positive, then I have a local min. And if there's no sign change at the critical number, then I have neither a max or a min. So this would mean if my sign chart looks like positive, positive, or something like that. An example of that last scenario would be a function that does something like this, where the derivative is 0 at this point, so we have a critical number at that x value, but the function does not change from increasing or decreasing there. It's increasing and then it continues increasing. Okay. So in the next video, we'll do 2 more examples of using the first derivative to determine where the function is increasing and decreasing.